Hi, everybody. I'm Rob, and Bujji and I are going to tell you about our work to bridge the gap between human cognition and silicone. This is work that we've done as part of the FARM and STACS group. That is the Predictive High Performance Architecture Research Mavens and the systems and technologies across the computing stacks. So at a high level, we will go over what neuromorphic computing means to us and how it guides our research practice. And then we'll talk about two different approaches we take through two different projects. One is top-down, which deals with deep noise suppression, and one is bottom-up, which deals with stochastic workloads. We'll conclude with the future work we have in store and our opinions of working with CHTC resources. So neuromorphic computing at a hardware level typically means taking the best of what silicone does at a computing level and how biological neurons compute. Silicone is very fast and very reliable, but the human brain is famously very power efficient. And so we try to take the best of both worlds and get very powerful algorithms that don't take that much power to run. And that's an interesting topic when we talk about machine learning, which is famously very power intensive. Again, so we also have the understanding of neuromorphic computing as a research guide. So from the top down, we try to understand neuroanatomy and how the brain works to inspire novel algorithms. And from the bottom up, we try to accelerate existing computing systems to understand how the brain works better. So to get into our top-down project, we studied the auditory cortex, that is the way that humans actually hear and transform wave signals from the outside world into neurological signals for deep noise suppression. Speech denoising is a very non-trivial but popular task, and there's two primary challenges out there that people contribute to. That is the Microsoft Deep Noise Suppression Challenge and the Intel Neuromorphic Deep Noise Suppression Challenge. So one is conventional, one is neuromorphic. If you're unfamiliar with what deep noise suppression actually is, the idea behind it is you have a waveform or just an audio signal, and it has a person speaking, but it also has some background noise. So you might have construction in the background, but you also want to make out what somebody's trying to say. And we know that artificial neural networks typically struggle with this task, and they are very power intensive, but ears are extremely proficient. So if you're on a call with somebody or if somebody's next to you on the street, you can hear what they're saying perfectly clearly, even though if there's traffic or construction going on. The famous example is if you're at a party, you can pinpoint on what somebody's saying in a group. So we try to get inspiration from how the brain does this in order to improve our ability to have a computer do this. So we have to pull up a model of the ear. One of the things that inspired this research very early on was the recognition that in the real world, speech and noise are rarely coming from the same point. You'll have, again, somebody talking to your left and construction happening in front of you. This matters because the pinna, which is the part of the ear that we're familiar with, will reflect those signals differently down the outer ear or the auditory canal and get transformed differently by the middle and inner ear. So noise will enter one way, speech will enter a different way, and they'll both get transformed differently. And this is due to a thing called head-related transfer functions, which actually change the waveform as they bounce through the auditory canal. Now, where does CHTC come in? We use a thing called the SIPC dataset, which keeps track of these head-related transfer functions from 1,250 different orientations. Now, I mentioned speech and noise, so two different waveforms taking two different positions out of 1,250 is a lot of different combinations, and that's where our workflow comes in. If we had it our way, this would be our workflow. We just submit a training job and we process it and get our results back. Unfortunately, we had to add a few steps in order to make our project actually run. The first thing was making a Docker image. You'll notice that the arrow here is green. That means that this part of our workflow is something that we manage. CHTC doesn't have anything to do with that. You'll also notice that V47 is bolded. We have had to iterate on this Docker image to get things working a lot. And it's 11 gigs when it enters the GPU lab machine. We then copy our GitHub repository down and its associated submodules. This allows us to do rapid development so that we can write code on our local machines and then silo off the processing to CHTC. And the big meaty portion of our workflow is copying over our data. So we have a shared directory that has 258 gigs of compressed audio files, and these get unpacked on the GPU lab machine and amount to 346 gigs. That's about 60,000 wave files of speech and noise that are separate. So this is one of the preliminary results that we found, and that has been powered by CHTC. This is the ability of the pinna to do deep noise suppression. So this is a heat map keeping track of what's called the SI-SNR score. It's basically the amount or the ability of a algorithm to recover the speech from the noisy signal. So in the lower right, there's a yellow blob. That means that the SNR score is high and that the speech was able to be recovered at a very good level, or at least a better level. And in the upper left is the darker blob, and that means a lower SNR score. Now, each one of these pixels in the heat map, it's a 50 by 50 pixel, takes about an hour to complete. And on the left axis is, the left side of the x-axis is when the noise is directly in front of the pinna, but 45 degrees below. And then the right side of the x-axis is when it rotates all the way around to the rear of the pinna. So at 90 degrees, the noise is directly vertical from the pinna. The same is said for the y-axis, except that's the speech. So we have two different things flipping around the ear in the same plane as the pinna. And the ability for us to recover the speech from the noisy signal varies drastically depending on those positions. Now, you might ask, well, why do we need this heat map? That seems pretty obvious. You can hear better when something is in front of you. This was just a sanity check for the downstream parts of our research, but we also wanted to compute this entire heat map because we wanted to see these macro patterns that only emerge once you've done a large amount of computing. Again, each one of these pixels took about an hour to compute, and because of CHTC resources, we were able to get this result in a matter of weeks instead of a matter of months if we were to do it locally. This is one of the more interesting results of our research. This is the same heat map, it's just color-coded differently, but it's the SI-SNR score. Bright indicates better performance, dark indicates worse performance, and this is the output of that pinna transformation from a spiking neural network. So this would be synonymous to getting processed by the actual inner parts of the ear. You'll notice that a lot more of this heat map is bright, and there's a red X down the middle of poor performance. Those are the times where the speech and noise are either mirrored about the pinna or co-located. Since we had to run these results through a spiking neural network, each one of these pixels took 4 hours to run. And again, through CHTC resources, we were able to get this result in a matter of weeks instead of many months. Again, we wanted to compute all of this because more interesting patterns emerge here at this scale of computing. Notably, this X across the heat map.
Cool. Thanks, Rob. Oh, yeah. So that was a talk about our kind of like ongoing and most recent projects dealing with. Oh, I think so, right? Yeah, okay. Can you hear me? Oh, that's better. Is that better? Okay. So an earlier project that our group had been working on is kind of starting from the bottom up. And so we were looking at these neuromorphic workloads from a computer architecture point. And what we noticed is that in these workloads and in other workloads that they are stochastic in the sense that they rely heavily on random number generation. And one insight that we found was that generating random numbers and using them in downstream operations, like conditionals or using data processing or data-dependent memory accesses, is very expensive in terms of CPU cycles that are wasted. So here, the red portions in each of these graphs represent generating the random numbers, and it's a significant portion of these workloads. More interestingly is probably the SGD application, which is a CPU version of stochastic gradient descent, and that's the one that excited us the most as well. But so in developing this, we wanted to come up with a CPU microarchitecture that could solve this problem and kind of accelerate these types of workloads. And going down the study, which a lot of it is outside the purpose of CHTC, but we realized we needed a way to compare the quality of these random number generation schemes. And that's where we found this package called DieHarder. DieHarder allows us to essentially determine the quality of a random number generator scheme. So we have a couple of different that we looked at in this study. Those of you familiar with random number generation, LCG is linear congruential generators. It's kind of like the first one that's taught in these types of classes if you ever learn about these types of things. On the right is ours that we've developed in this research direction. So this is a cool plot. It shows you basically the DieHarder test suite has about 114 tests that they run to determine the quality of a random number generation scheme. This plot was actually generated with our own lab machines, and we realized that if we wanted to scale this and evaluate this in a more thorough way, we really needed more compute power. As you can see, each trial of the DieHarder test suite takes about 6 hours. So, and we ran 30 trials across 6 different random number generations. So generating this took really long and was very painful. So we had an idea of what we wanted. This was our first project trying to use CHTC, and we really wanted to leverage the CPUs, the CPU cluster here. So for this, I think the problem mapped really well to what CHTC resources could provide. We developed a lightweight Docker image with DieHarder installed. We had single CPUs that were requested and small memory and storage requirements. We had one caveat that we needed certain modern CPUs, but that was an easy requirement to enact. And so this mapped really well. We were able to develop this next plot that I'm about to show, which basically shows how good our RNG strategy is. But I think the thing to highlight here is that this on our lab machines would have taken about 2 years to finish, whereas with CHTC resources, it took about 3 weeks, which is pretty cool. So this is just the results of those plots. Here we're reseeding, and basically we see that the random number generation scheme that we developed in this research is just as good as the best of them. Now I know this is the running GPU or running AI ML and stuff on the GPU clusters, and something that's interesting for us is we want to evaluate this feature on different types of GPUs. So that's where we're going with this work and why it relates to this part of the talk. Okay, so that's pretty much a wrap up for the 2 projects that we have ongoing using CHTC resources. Just some overview and current outlook and what we plan to go on into the future. From our perspective, CHTC has been really easy to use. We've actually really enjoyed using it, and I feel like the staff has been very helpful in troubleshooting our bugs. We did have some minor pain points using the GPU system, but again, they are minor, and they haven't been prohibitive for us to develop. Probably the most annoying part of this is we've ran into some issues where the GPUs crash in an unpredictable way while we're running our experiments on the first half. So we're still investigating why this happens. Some features that we know that CHTC supports that we really do want to try to look through and kind of implement in our own workflow is the checkpointing. This is something that's really interesting for us because we have some long sims that we really want to try running. Queuing up and modeling or sweeping of model hyperparameters, that's really interesting to us because, as we mentioned, we have a lot of different types of things we're trying to configure and run through. And we know that our flow is it was something we got working. We know that there's a lot of inefficiencies there, so we're really interested in trying to do some better workflow orchestration as well. And one thing that we thought would be cool from CHTC in the future is to support a variety of vendors on their GPU clusters. So I think right now they do support a lot of different versions of NVIDIA GPUs, but it would be really cool to do have other vendors like AMD GPUs as well there, so we could do a vendor-to-vendor comparison.
For the last point, I don't know, Brian, do we have in the OS pool AMD, access to AMD?
So there is the NSF funded an AMD MI300A system to be deployed at STC. We're just in the process of procurement.
Very cool.
So this will come up eventually. And HTC24 was part of the science drivers because the system is meant to accept, I think the tagline is no software left behind. The notion that to help community software products transition to AMD GPUs and transition to GPUs in first place. And
Very cool. Yeah, I'm excited when that happens. I know that I think there's A100s right now, even H100s. So a comparison to the MI300 would be a nice.
Yeah, and that should encourage you to do the checkpointing work.
Right.
Because with good checkpointing, these kind of resources become more available to you.
Right. Thank you. But yeah, thank you for listening to our talk.